go.
Welcome back to the conference, and now it is a great pleasure for me to introduce a talk which is isoperimetric and partitioning problems. And the speaker of this talk is a Williams College professor, faculty member, and also the chief editor of the Notices of the American Mathematical Society. So please welcome Frank Morgan.
Thank you very much, Paulo. It's great to be back here in São Paulo. Have this chance to talk about isoperimetric and partitioning problems. In particular, I'm going to focus on the double bubble. But we have to start with a single bubble, which today is just going to mean single bubble, which today is just going to mean. Yes, we'll get moving here in just a second. Why doesn't this move now? There we go. Well, I don't know if that was good. Single bubble in the plane, for example, is just trying to enclose given area with minimum perimeter. And of course, the way to do that, is just with a round circle, which you can prove by symmetry. And similarly, if you're in three-dimensional space, the ideal bubble is a round sphere. As was demonstrated by the soap bubble millennia ago, long before it was proved by Schwarz in 1884. And the same thing is true similarly in higher dimensional space, Rn, in n-dimensional spheres, in n-dimensional hyperbolic space, and conjecturally, as I mentioned in the open problem session, in CP2, so there's one of the open questions I wanted to mention. It gets more interesting, however, R2, if you put some density on the space. Here I pictured Gaussian density, which drops off like e to the minus r squared exponentially as you move away from the origin. A density that has lots of applications, and even in particular one to the Perlman's proof of the Poincare conjecture. So the density here gives the space largest density. Most of the mass is concentrated around the origin, and then as you move away from the origin, the space gets very rarefied. That funny factor of 2 pi there on the front is just to give the space total weighted area 1, which is the nicest it could be. And then the single bubble in Gauss space is looking to enclose given weighted area with minimum weighted perimeter. So the weight applies equally to the area and to the perimeter, something much simpler than a conformal change where you might multiply length by lambda and area by lambda squared and volume by lambda cubed. A simpler, very easy thing to think about. Here, we still have rotational symmetry, so you could probably guess pretty quickly that the solution ought to be a circle about the origin. And think about it. If you move the circle a bit away from the origin, then since the density is going down, it would have to be bigger to have the same weighted area. So the perimeter looks bigger, but then the density is smaller, so that reduces the perimeter. And actually, you do better than a circle about the origin. You do better if you move away from the origin, because perimeter does not scale up as fast as perimeter as fast as area scales up. So you actually do better by moving away. And this is a principle that soap bubbles like regions of low density, not high density. And now, so then what is best? Right? You can't move all the way off to infinity. There's not enough area out there. Not enough weighted area out there. But there is an optimal bubble shape, and it's a shape you've heard of. I don't know if anybody who doesn't know wants to guess. In Gauss space, this wonderful space of total area 1, the optimal bubble is not a circle, but a straight line. Straight line, the only thing simpler than a circle, this straight line which encloses some finite fraction of the area 1 on its right. If you wanted to enclose less area, you just move it farther to the right. If you wanted to enclose more area, you move it farther to the left. It's not unique. It wouldn't have to be vertical. It could be horizontal, or it could be diagonal at any angle. So it's a great example of symmetry breaking. It was actually proved back in 1975, although the uniqueness result only goes back about 15 or 17 years. And in higher dimensional Gauss space, similarly, the optimal bubble is a hyperplane, nice as could be. And this result actually figured specifically in Perlman's proof of the Poincare conjecture. And the original proof, just to give you an idea, used the fact that you can get Gauss space down below there as a limit of projections of high-dimensional spheres. And the reason then that the line is minimizing down in the Gauss plane here is that its inverse image, a circle or a sphere up in the big sphere above, is known to be minimizing up in the sphere. Actually, Gauss space is the most important of the spaces with density. And in fact, in this category, it replaces the sphere, dethrones the sphere as the model that you compare every other space to. So I mentioned there's been a huge flood of interest in densities, and in particular the isoperimetric problem since their appearance in Perlman's proof of Poincare. I try to keep a list of recent papers on my website, and it's hard to keep up. There have been over 100 since 2016. At a big conference in Montreal, I asked some of the young experts why densities are so important, and Robert McCann said that, well, even if you want to just start with density 1 classical manifolds, in the limit, you're going to get other densities. Yeah, this is what Robert had to say to me.
I guess manifolds with density can arise as limits of manifolds with volume, in which some dimensions collapse, and you get an accumulation of mass in those areas where you have collapse. They also give a nice model for other manifolds. For example, you can put Gauss measure on the Euclidean line,
Gauss.
and it behaves in many ways like a positively curved manifold, like a sphere.
And I asked Emanuel Millman, and he similarly pointed out that you can get densities by taking projections of classical manifolds. And again, he mentions the example that I talked about before. You can actually get Gauss space as a limit of high-dimensional spheres. This is what Emanuel Millman had to say.
I was thinking about why manifolds of density are interesting. So they're interesting because they appear as natural closure of usual manifolds under measured projection. Okay, so for example, the Gaussian is well known to be a projection of a high-dimensional sphere, and of course you want to include the Gaussian measure in anything you study.
Yeah, the Gaussian is certainly the most important, this e to the minus r squared. It's also interesting to look at the opposite kind of density, though, like e to the plus r squared, where the log plus r squared is now convex as compared to e to the minus r squared, where the log is concave. And here, the density is smallest at the origin. Bubbles like to be around the origin. And the 15-year-old conjecture said that for log convex densities, radial, spheres about the origin are optimal. And this was just proved. It's a proof. It should be published shortly this year. It was proved by Gregory Chambers, who at the time was a graduate student at the University of Toronto. He's now at Rice University. And the proof, well, it started with symmetry arguments, of course, as they all do, but then it was a very straightforward use of delicate estimates, one after another, not using anything super tricky and elegant as other mathematicians had tried and failed. I went hiking with Greg in the mountains around Williamstown, and I asked him about this proof he had come up with, and this is what Greg had to say.
So the proof of the log convex density conjecture first involves reducing the problem down to axially symmetric minimizers and then examining the generating curve. So from a first order formula, you can produce an ODE for this curve, and you can show that if it's on an upper half circle, it has to spiral in too quickly. But what's fascinating is that the estimates involved in proving this are actually very delicate, surprisingly delicate.
Thanks, Greg. But today, we're going to focus on the double bubble. The double bubble, which tries to enclose and separate two given volumes with minimum perimeter. And the conjecture is that it's just the standard double bubble that you always see if you try it with soap bubbles. Maybe I can try it here. So there we have a lot of bubbles, but if two come together, you get this double bubble shape, which consists of two spherical caps with a separating surface, which is, in this case, pretty flat, but in general will be a third spherical cap, all meeting at 120-degree angles. So that's that beautiful conjecture. It actually first appeared as a conjecture in an undergraduate thesis by Joel Foisey, who was the first one to realize that it was open. A lot of people thought it was something that was known. And I asked Joel what it was like to see this conjecture, which first appeared in his undergraduate thesis, attract so much attention and work by mathematicians around the world. And this is what Joel had to say to me.
After the double bubble conjecture appeared in my thesis, and then I started hearing reports about how progress was going. It was exciting to hear that people were making progress on it, and I was happy. A small part of me was a little bit, I don't know, envious isn't the right way of word, wistful of, wanting to participate and be part of that.
So he said he wanted to be part of all the research, but of course he was an important part of it right from the beginning, and he now has his own group of students working on new open problems with him at SUNY Potsdam. So this is a beautiful shape, this double bubble shape, the three spherical caps meeting at 120-degree angles. Two separate bubbles, are very wasteful because it's more efficient for them to come together and share that common wall. What else could a double bubble look like? Well, bubble inside a bubble. That's even worse because when you put the bubble inside, it forces the second one to be bigger. If you just take it out, it could be smaller, and then when they come together, it would do still better. So this is why you never see a bubble inside a bubble, although I always try. I think it happened once by accident. But oh, it's a little windy here, too. So, you're never going to believe it ever happened. Yeah. You're not going to see it here today. Not that anyone ever sees it. So, I knew you wouldn't believe it. So, I brought a picture. There was the time it happened, actually. Here's a close-up. You can see for a moment this bubble inside a bubble. When it comes down and rests, though, on the outer bubble, then it pops out. It's an unstable configuration. So that bubble inside a bubble. But there are other possibilities, actually. Now I'm going to show you a computer simulation of a very weird non-standard double bubble, a computer simulation by John Sullivan. You ready for this? It's very strange. Okay, here it comes. There's a bubble on the inside with another bubble wrapped around it in an inner tube-like shape, like that. So this is unstable and has more area than the standard double bubble, but it does make you realize that there may be other possibilities which neither we nor the bubbles have thought of yet. Here's a better picture where you can see how narrowly the waist of that interior bubble gets squeezed by the toroidal inner tube around it. So that would be worse. Maybe it could be lopsided. The inner tube wouldn't have to be centered. And maybe if that could happen, maybe the blue region at the center could have a second component to it. A skinnier inner tube wrapping around the red inner tube, wrapping around the central blue bubble. Connected by a thread of zero area, if you like. Actually, in this context, connectedness doesn't have any real significance. And if that could happen, maybe you could have layers of inner tubes on inner tubes on inner tubes. Or maybe you could have the bubbles knotted around each other somehow. Or maybe the thing could be fragmented into millions of components, maybe even with some empty space accidentally trapped on the inside. So this is sort of the low point of the talk. It looks completely hopeless. But there were some things we knew right from the beginning. It was Brian White who pointed out to me that the minimizer has to be a surface of revolution. Now, symmetry arguments are so important, and this one's kind of useful, so I thought I'd just tell you about this symmetry argument, that the minimizer has to be a surface of revolution. And it all starts with this lemma, that some vertical plane splits both volumes in half. All right, so over there is the double bubble, the minimizer. And I can take a vertical plane and I can march with it until it splits the first volume in half. But it probably hasn't split the second volume in half. There's probably more of the second volume in front of me. Well, maybe I started at the wrong place. I'll start back here and stop walking in until I split the first bubble in half. No luck. I didn't split the second bubble. Well, I can keep trying this at every angle till I come around 180 degrees and move until I split the first bubble in half, which I did before with this plane, but now the large part of the second bubble is behind me. So by the intermediate value theorem, there had to be some starting angle where when I split the first bubble in half, I would also happen to split the second bubble in half. So there we get a plane that splits, a vertical plane that splits both volumes in half. Now I turn the picture over 90 degrees, making that a horizontal plane, and I repeat the argument, and I get a second plane perpendicular to the first plane that splits both volumes in half. We might as well assume then that they are the xz planes and the yz planes, which meet along the z-axis, which maybe you can guess is going to be the axis of rotational symmetry. And now we can assume that the xz and the yz planes, it'll turn out, we can assume that the bubble is symmetric across these planes, because if it's not, you can take the cheaper half and reflect it across this plane and get a better bubble that's symmetric across the plane. So we now have symmetry across the xz and the yz planes. If you compose those symmetries, you get symmetry under 180 degree rotation, which means that every plane through the z-axis splits the volumes in half. So every vertical plane now splits the volumes in half. And that means that the bubble has to be perpendicular to all those planes, because if it meets it at an angle, taking half and reflecting across will give you a corner, and you can always smooth a corner and reduce area. So it's perpendicular to all these vertical planes. Well, that means it's always tangent to the direction of rotation, and it must be a surface of revolution. So there's the symmetry argument that the double bubble has to be a surface of revolution. Well, that was sort of the starting point. It was about 10 years until we had a proof that the double bubble, the standard double bubble, was better than all these crazy alternatives. Better than all these crazy alternatives. And I'll just tell you the main idea of that proof was an instability argument, and I'll tell you how it works with our favorite kind of example here, where we have a bubble in the center and a toroidal yellow inner tube wrapping around it from top to bottom. So that yellow thing, that's one inner tube wrapping around it top to bottom. And the argument that you use here now is you turn the left half to the left and the right half to the right, and the top gets fatter and the bottom gets skinnier, but the volumes are maintained. But at the little points where you do the break, you create little cusps which can be smoothed to reduce area to second order. So that's the idea of the instability argument. That's the idea of the instability argument. It only works here, though. In this case, I did it when each bubble was connected. Both regions of prescribed volume were connected regions. And to prove things like that, there was a whole theory developed by one of my former students, Michael Hutchings, who had this little test. He said, look at this function, and if it's positive, so a region of volume fraction V is connected if this function of V is positive. V is just a fraction, and it involves just looking at the least area for a single bubble of volume V, and a least area of a single bubble of volume 1 minus V, the complementary fraction, and a least volume for a single bubble of volume 1. And then there is one double bubble involved there, the least area for enclosing volumes V and 1 minus V. Now, we don't know what that is, but since that's a negative term, we're happy to estimate it from above with the standard double bubble. So that's then is a formula, an estimate that you can compute, and if it turns out to be positive, you know the component's connected. And in R3, that turns out to be true most of the time, as long as the component has at least 20% of the total volume. So that was most of the cases, and if one of the components had to be very small, it took another special argument that I don't want to talk about. But so that was the key to the proof in R3. And then an amazing feature was that summer, right on the heels of our work, my geometry group, undergraduates, proved the same result in R4 by realizing that they could generalize the argument and only need one, the larger bubble, to be connected, which was always true in R3, giving an easier proof in R3, and was always true in R4, giving a proof in R4, and failed to be true in R5, so that they could only get certain cases on R5 when the larger bubble, when the smaller bubble was big enough, So Ben Reichert was the one who led that effort, and I asked him what it was like to work on that problem. This is what Ben had to say.
I wrote down all the possible alternative minimizers in R4, about 200 of them, and eliminated them individually or in small groups to leave just 2 or 3 unresolved problem cases. But instead of finishing the proof off, the next week I got more ambitious and tried to classify general cases in higher dimensions. I eventually found a single case in R5 which could not be eliminated by our method.
So got stuck in R5. Too bad. All right, so that's where the double bubble was. It was stuck in R5. Meanwhile, some groups of students were working on extensions using these methods to the 3-sphere and hyperbolic space. And they just looked at the Hutchings function. Whenever it said that both regions were connected, they could apply the machinery and conclude that the standard double bubble was best. And this turned out to work in S3 as long as the 2 regions and the complement, S3 has finite total volume, were all at least 10%. And in H3, it worked when the smaller region was at least 85% of the larger region. That was enough to apply the Hutchings theory. They just had to verify the Hutchings inequality numerically, check that a certain function was positive. Here's the sketch they did for S3, for example, and you can see most of the time the blue graph is above the floor once you get past that 10% line. But now, of course, if you wanted to do this in general dimension, you would have to repeat that numerical computation in every dimension, and it gets harder and harder the higher the dimension. So that was a problem. There was no idea how to do anything for all dimensions. Meanwhile, I had other students working on the double bubble problem in Gauss space. So there were a couple years when they were working on that. Remember the Gauss plane where the single bubble was a line? The double bubble is not 2 lines. You might think it's 2 lines. It's not 2 lines. But it is still rather linear by conjecture. The conjecture is that it's 3 half lines or half hyperplanes in higher dimensions meeting at 120-degree angles. So that was the Gaussian double bubble conjecture. And the good news about Gauss space is that the Hutchings estimate, all you have to do is check it in 2D. That proves it for all higher D, because everything is a product in Gauss space. Everything is flat and a product. So that was great news. But the bad news was that the whole machinery doesn't work in Gauss space because you don't have enough symmetry. You don't have translational symmetry as you have in Euclidean space and on the sphere and in hyperbolic space. So the argument didn't work at all. And then Joe Corneli here, who was an undergraduate at the time, had the idea of proving the double bubble theorem for the sphere and Gauss space simultaneously. They're related, remember, because Gauss space is a limit of projections of high-dimensional spheres. And his idea was to verify the Hutchings inequality in G2, in the Gaussian plane, which would then imply it, and then carry out the proof, I'll do this in more detail in a minute, in the sphere, and then translate the result back to Gauss space. So in a little more detail, you showed that the Hutchings function is positive in the Gauss plane. That means, since that's the limit of projections of high-dimensional spheres, that means that it's positive in Sn for large n. But since large n's are harder, that means it's positive in all Sn for all Sn, and that means the best double bubble in Sn is the standard one. And now you go back and look at Gm as the limit of high-dimensional spheres and conclude that the best double bubble in Gauss space is hyperplanes meeting at 120-degree angles. And this worked whenever the Hutchings inequality worked in G2, which was when the volumes were nearly equal, all varying from about 0.3 to 0.37. So at least for those cases, there was a proof of the triple bubble conjecture in Gauss space. But all of these things only worked in the limited context for those particular fractional volumes where that Hutchings estimate told you that the regions were connected. So that was a real drawback. Proofs for all volumes require a different approach, and that's been much harder. The first big project in 2008, about 8 years later, Reichard went on and was able to prove the double bubble conjecture in all dimensions, in Rn, for all volumes. And the way he did it was avoiding the connectedness lemmas altogether by proving it, by making the instability argument work, no matter how many components each region had. Necessarily finite by the regularity theory. But he got it to work when you had tori on tori on tori and tori, trees of them going on for any finite number of stages. So that was really a tour de force and very intricate, and no one has ever managed to extend it to any other spaces. So, but Euclidean space, it's proved in all dimensions. And then there was no progress until this year. So it was just this year that Emanuel Millman of Technion and Joe Neiman of the University of Texas at Austin, it's just appeared in the archive, not published of course, in January, proved the double bubble conjecture for any 3 volumes in Gauss space of any dimension. Now there are 3 volumes, right, because there's a finite volume space, so you have the 2 regions of the double bubble and you have the complement. That's why there are 3 regions. And so they proved that result, and they did it using, at basis, a familiar method. And that method is to just look at what's called the isoperimetric profile. That is, the least possible perimeter, here I'm calling it P0, as a function of those 3 given volumes. And of course, what we're conjecturing is that that's smallest for the triple junction there of 3 half-planes, which I call P sub t. And all we know to begin with is that the minimum is less than or equal to the conjectured value, and we'd like to prove equality. The conjectured value has the virtue, conjectured value, which is over here, has the virtue of the pieces being flat. The actual minimum, we know nothing about it. Curvy, I've illustrated here, and probably much more complicated. Maybe many components, we have no idea what it looks like. But if you just think of the graphs, all we know is that the blue graph lies above the red graph. At the extremes, they get small. The extremes are when all of the volume is concentrated in one of the bubbles, which is very nice. Then you just get one big single bubble. It's most expensive in the middle, where it's kind of evenly divided among the 2 bubbles, and it's higher in the middle. So there we have, that's what that's all we know. The picture looks something like that. This red graph lying above this blue graph, both of them with negative second derivative. Both of them preferring to move away from that center position. Well, now the key proposition that they had is that P0 has a more negative second derivative than PT. And the idea for proving that is that curviness leads to instability. If you ever look at the second variation formula, you can see that curviness contributes to the negativeness of the second variation. So that was the idea of that little lemma. Well, that contradicts the picture, right? In the picture, the red one has more negative second derivative. But here's this contradictory proposition that says the blue one has more negative second derivative. So the only way you can resolve that is if they coincide. So that was the idea, the starting idea of their proof. But the details get very technical, very complicated. I'm worried about what I just said because this is really a tremendous contribution. And we've been waiting years for this. Tremendous contribution. And then there was another news bulletin just 2 months ago on the archive in May in which they did not only double bubbles, but triple bubbles and quadruple bubbles and quintuple bubbles. That is dividing Gauss space into Q regions as long as the dimension, as long as Q was less than or equal to 1 more than the dimension. So that would be, you could have 3 regions in the plane, or 4 regions in space, as we have here, and there the solution is the cone over the tetrahedron, dividing space into 4 regions corresponding to the 4 faces of the tetrahedron. Just down in the plane, those 3 half lines meeting at 120-degree angles was the cone over the triangle, cone over the tetrahedron. In higher dimensions, if you just want to keep 4 regions, you just cross this picture with a line. If you want to up both the number of regions and the dimension of the space, you use the regular 4 simplex, the cone over the regular 4 simplex. So there's this wonderful family of solutions that have been proved for solving the multi-bubble problem in Gauss space of all dimensions. And it was an extension of their previous proof, except now, I said the technical details were bad before. Now the technical details are so problematic that they don't even want me to call them technical details. They said, no, they aren't technical details. It's like a whole new problem requiring whole new ideas. But from our bird's eye view, we can think of them maybe as the technical details. So that really kills it in Gauss space, which turns out to be the easiest space to work in. Although, for example, if you have more regions than 1 more than the dimension, for example, if you have 4 regions in the plane, that case remains conjectural. Here's what we think it is. We think it's this double Y shape, which has 2 vertices where 3 lines meet at 120-degree angles. And now you want to vary, you want to get all possibilities for 4 areas, but you can do that by moving this around and turning it and stretching the center line. And that gives you all the possible 4 tuples of areas that you could have. And that's the conjectured minimizer. And this, I think, would be a great student problem. That's open. Of course, in Euclidean space, we know even much less. The triple bubble in space remains stubbornly open, and it looks like a proof could be very far away. It was hard enough getting the triple bubble in the plane. That was a PhD thesis that involved hundreds of cases done by Wacharnwichy Ramala back in 2002. Okay, now I have a question for you guys to see how you're doing. You know, halfway through a lecture, you're supposed to give like a pop quiz. So here's your little quiz question. Do soap bubble clusters actually find the least area shape? Now there are 3, this is a multiple choice test. There are 3 possibilities here. A, yes, always. B, no, not always. C, no one knows for sure. And you guys all have to vote. Everyone has to vote. You have to commit to one or the other. So here we go. How many people vote yes, soap bubbles always find the minimum configuration? All right, Carlos says yes. How many people go with B, no, not always? That looks like a minority, but a good minority. They may get a seat in the council. And how many people go for C, no one knows for sure the answer to this question? Well, that's an equal minority. The abstainers could have swung it either way. They missed their chance. Well, the actual answer is B, no, not always. Here's a counterexample consisting of 2, 5 bubbles with the same 5 volumes. The only difference is where the tiny 5th volume is placed. In the bubble cluster on the left, it's comfortably placed among larger bubbles. In the bubble on the right, it's less comfortably situated among medium-sized bubbles, with the result that the bubble cluster on the left has slightly less area, even though they're both perfectly stable, fine bubble clusters, happy with their lives as they find them, but one is actually better than the other. And then you can ask, is that one on the left actually least area? Someone says no. Reason? Doesn't have a reason, but he was right. No was right, because it would be even better to put that tiny 5th volume in back, where it would be even more comfortably settled among the 3 largest bubbles. That would be even better. And then, is that the best? Well, I think so, but it's hard to know for sure. Nobody knows. Nobody knows. Okay, now let's look back at log convex densities, the sort of other extreme case like e to the plus r squared, where remember, this theory of Gregory Chambers said that the single bubble is a sphere about the origin. So let's just look at R2 with this density and look at the double bubble problem there, which again, remember, is to enclose and separate given weighted areas with minimum weighted perimeter. Now, I had my students thinking about this. Not much was known about this. Not much was known about this. Of course, the bubbles like to be near the origin, where the density is smallest now. Density is smallest around the origin. So for small areas, you'd expect it to look a lot like the standard double bubble, because very near the origin, the density is close to being constant. Although as you start to move away, it increases very rapidly. What happens for larger areas? Let's just say equal areas for now. Well, they did some numerical studies, and they got these weird elongated double bubbles. Yes, that's the expression I had right there. Little perplexity. Because, you know, that didn't seem right to me, because I thought that since this density is growing so rapidly, the double bubble would want to stay inside the smallest sphere it could, and it would be something like a sphere divided in half by a diameter. That's what I thought. So who do you think was right? My friends. You think I was right. You think I was right. This time I was right, and they admitted it. Yes, this time I was right. There was a mistake in their program, and when they improved the program, they got something like that picture on the left. And then when they did larger volumes and scaled it down so you could see it, they got a picture more like this. And when they did still larger volumes, they got a picture like this. So I guess my intuition on that one happened to be exactly right. This is what Leo had to say about that.
We spent a couple weeks looking for the double bubble in the Borel plane. In the beginning, we found some strange oblong and pointed shapes. But at the end of the day, Professor Morgan's intuition of a more rounded double bubble turned out to be correct.
Well, thank you, Leo. He's such a good sport. Now, those were equal areas. What if you have unequal areas? Well, this was kind of fun. Apparently, when you have unequal areas, you sometimes get a bubble inside a bubble. That thing which never occurred in Euclidean space apparently occurs here. So that's what the numerical evidence supports. And they actually analyzed this, killed the analysis actually, in 1D, and showed that the solution is not adjacent intervals as you might always expect, but sometimes the blue interval inside the green interval. So they proved that, and they carried on much more analysis actually. Here's a graph that shows exactly what happens for a smaller volume V1 and a larger volume V2. This is for the density e to the r squared. And you can see for any, that red line is the line of division between what they call the double bubble, the expected standard adjacent intervals, and above that, the triple one, which is the blue one inside the green one. And they analyzed the tie curve, where double and triple tie. And you can see that for any, no matter what size the smaller bubble is, if the larger bubble gets big enough, then you get this transition from the adjacent intervals to a bubble inside a bubble. And in fact, there's some very interesting behavior. If you go along that line there, you see it labeled V2 equals 10 V1. So that you can see this better, the V1 scale is different from the V2 scale. You see V1 scale goes up to 10, the V2 scale goes up to 100. So that line at 45-degree line is V2 equals 10 V1. Now, let's keep them in that ratio and just scale them up. When they're both very small, of course, as we observed, it ought to just be the standard double bubble, the adjacent intervals. But then as it gets larger, it doesn't take long for that line to cross the red curve and to enter the bubble inside a bubble range. And then what's even more strange is that eventually, as they get even bigger, it returns to the standard double bubble of the two adjacent intervals. This was complete. This is one where my guesses were completely wrong. I thought that the behavior would be kind of monotonic, and that was wrong. It wasn't at all. There was this reversal of behavior. So this is a very typical picture here. There are actually three kinds of behavior. It's also possible, they discovered, for the red curve to blow up in finite time, so that for large values of V1, no matter how big V2 gets, it stays standard adjacent intervals. And in fact, there's even an extreme case where it's always standard adjacent intervals, no matter how big either volume is, still for a strictly log convex density. So all three of those things occur. This bubble inside a bubble, though, was quite surprising. Dillinger was surprised.
In the Euclidean space, the least perimeter way to enclose two given volumes is the double bubble, or when two bubbles come together. But once we throw a density of e to the x squared on it, some strange things happen. On occasion, we think we get a bubble within the bubble, which can never happen in Euclidean space.
So this work is pretty new, but it was just published earlier this year in the journal in Analysis and Geometry in Metric Spaces. Yeah, so there it is. Some of the authors. Our trip to the beach, my favorite place. I have a lot of fun. And we have a lot of students actually over the summer from around the world working on projects like this, about 30 maybe, including my group of 4. Applications are due in early February, and maybe some of your students will come next summer. That would be fun. There are actually almost 100 undergraduate research sites in the United States now, although only a few of them are open to international students. Well, we've looked at bubbles, double bubbles in Gauss space, e to the density e to the minus r squared, in Borel space, e to the plus r squared. But where's the most fun place to look for bubbles? In a torus. So that'll be our final playground here, looking for bubbles in a torus. So we'll be looking at first of all, a flat two-dimensional torus. You can just take a rectangle or a square and identify opposite sides. And then the best single bubble is not hard to find. It was first written down in an undergraduate thesis. For small areas, it's a circle. And then for larger middle-sized areas, it's a strip. And then for big areas, it's the pink complement of the circle. So that was written down in the undergraduate thesis of Hugh Howard's. But what about the best double bubble in a two-dimensional torus? Well, again, for small areas, it ought to be just a standard double bubble. And Joe Masters, in his thesis, suggested some other possibilities. For large areas, it ought to be what you see in the lower right-hand corner there, just two strips and the complement a strip. And then if one bubble's big and the other one's small, it's sort of a strip decorated by a bubble, as in the upper right there, as you can see. And then he imagined that you might get this fourth possibility, a chain, if they're kind of small but not too small. So that was his imagination. So do you think you get this chain ever? Well, we had some students that really analyzed this one in the succeeding years, and yes, you do. You get that chain. So there are, in general, those four possibilities. There were other possibilities they had trouble ruling out. For example, octagons and squares, which you'll find often. The first time I gave a talk on this, they were right in the bathroom there. Octagons and squares do a nice tiling, but they do not solve this problem. So those are basically the four types, and then you can ask which type you get for which areas, and that's shown in this colorful picture there in the upper left. That's the picture for the square torus. On the edges, one of the areas goes to 0. So at the vertices, two of the areas go to 0. So two areas very small, and that's when you get the red standard little double bubble in the corners of the triangle. Otherwise, along the edges, where just one of the areas is small, you get that decorated strip. That's the green picture, the decorated strip. And then there are those yellow regions where two of the areas are kind of small but not too small, where you get that chain. And then finally, in the middle, where the three areas are all pretty big, you get the double band. And they analyzed this for all of the flat tori. The most interesting and special one was the second one on the top row, there in the upper right, where you see that this is the one where you have it's a parallelogram with a 60-degree angle, also known as the hexagonal torus, because you can get it by taking a regular hexagon and identifying opposite edges. And in that case, the double strip has to share its glory with a tiling by 3 hexagons. So it's actually possible, as you can see in the bottom picture on the left there, to tile this special hexagonal torus with a green hexagon, a blue hexagon, and a white hexagon, all having the same area. And that's a tie with the double strip. So that was the complete picture. And of course, they made these by just doing some numerical calculations, just comparing the different ones. There was the graph. You can see sometimes the band length beats the standard, little standard bubble, and sometimes it doesn't. And you can sort of see very clearly where they cross. Okay, so that was preparatory for thinking now about bubbles on the 3-dimensional torus. And we're going to just stick with the cubic torus and start with the single bubble. So what's the best single bubble on the 3D cubic torus? Well, if the volume is small, it's going to be a little ball. So the volume gets bigger, it's probably going to be a cylinder. Remember, the top and bottom are identified. And if the volume gets still larger, it's probably going to be a slab. Remember, the edges are all identified. The front and back and the left and right are identified. And that's the conjecture due to Rittore and Ross of Granada. That's the conjecture. But it's an open problem, as I mentioned in the open problem session. It's very delicate. It's only barely true, if true at all, because, here I'll show you a picture from one of Ross's papers, and this just shows by symmetry an eighth of the picture. So you just see an eighth of the picture. On the top you see the eighth of a little ball, the eighth of a cylinder, and the eighth of a slab. And down underneath you see some competing surfaces of Lawson and Schwartz. And that Lawson surface comes within 0.03%, not 3%, 0.03% of beating the cylinder. So that's how delicate the problem is and what makes it so hard to prove. And in fact, Ramon has observed that if you take a skew cube instead of the cube, if you skew the cube a little, then Lawson's surface actually wins by 0.02%. So you have to worry about all these weird competitors. But for now, let's assume that the conjecture is true, that the solution is either a little ball, a cylinder, a slab, or a complement of a cylinder, or a complement of a ball. And ask, what's the best double bubble on the 3D torus? So I had a school of graduate students out at Berkeley one year working on this problem, and they started up by just making guesses, right? So they said, well, let's think about it. You can have a little standard double bubble, or you can decorate a cylinder with a little bubble, or you can have a double cylinder, or you could decorate a slab with a little bubble, or you could decorate a slab with a cylinder, or you could have a double cylinder. And they wondered if all of these had their moment of glory, if they would all win sometimes. So how many of these 6 do you think actually turn out to beat the other 5? Yes, it's all 6. All 6 do. So they did a chart comparing, and yes, they all had their moments of glory. And so this encouraged them to pursue this for quite a while. It turned into a nice paper in the Journal of Experimental Mathematics. And in the end, they actually had 10 winning types. And they're the 6 that we described, and also some more complicated things. Look at that cylindrical cross in the middle of the second line, where you have one cylinder going one way and another cylinder going the other way. Or in the middle of the next line, where you have this bubble in the center of a slab. So those were kind of fascinating ones. And later on, when I was visiting, giving a talk somewhere, the students there got interested in trying to create these with bubbles. And so, for example, they actually produced, there it is, the chain. There's the cylindrical chain. They got that just in a plastic cube. There it is, that Delaunay chain they got in the plastic cube. And they got all of them, actually, including, I'll show you some of these funny ones, the center bubble and the slab cylinder. So there's the cylindrical slab, which they got with soap bubbles. And there's the center bubble. That was the hardest one for them to get. So they all appeared. Of course, the authors of the original paper liked them a lot. And now again, you can ask, when does each type win? When does each type win? Well, instead of once again, there's a triangle of possibilities, right? There's a triangle of possibilities. Each edge of the triangle is for one of the volumes being small, and the corners are 2 of the volumes being small. And look at this elaborate picture that you get. You can see up in the corners you have the standard double bubbles. Those are the yellow ones. And in the center you have the double slab. That's what happens when the volumes are all approximately equal. And all the other possibilities have their moments of glory in this phase space there, the double bubble. So isn't this a great picture? What does this make you think of when you see this? Well, what it made them think of, I was very glad for, because one day in my office I got a big package marked delicate, and they had turned this phase portrait into a stained glass window, which I had for many years hanging in my office. There it was, reproducing that phase portrait for the conjectured double bubble in the torus, in the cubic torus. By the way, not every possibility they tried type, so they thought maybe, how about 2 cylinders just brushing against each other? No, that didn't work. Or this, look at that center cylinder in the lower left. No, that didn't work. Those were losing candidates. So that's what left them with the 10 winning types. But of course, this is just a matter of numerical comparison of everything they could think of, right? So there's no rigorous proof there. And this, I think, of all the open problems I've mentioned today, is by far the hardest. I wouldn't suggest it to anyone. I mean, we can't even prove the single bubble in the cubic torus. Here is the conjecture for the next century. Try to prove the best double bubble in the cubic torus. May some of us live to see that. I don't know. Thank you very much.
Let's ask Frank some questions. Who has one? Okay, I'll start with one. Can we make with soap bubbles, can we make a surface with higher genus?
With soap bubbles, can you? Oh yeah, so that's sure. Just take a twisty wire and that'll happen. You'll get a surface of higher genus. I should have brought some wine. Yeah, we will. Next time we'll have a lab here. We'll have a soap bubble lab.
Okay.
Yeah.
I'd like to see that.
Now, without wires, you mean? Can you get higher genus? I did. Tom Noddy made a torus, but it's unstable. It doesn't last that long.
It doesn't matter how. I would like to see one.
Yeah, you'll like to see one. Now you're going to have to invite me back, and we'll do it. Yeah.
Sure.
This is good. This is working out well. I like this question session.
It was almost the same question. Can you solve the bubbles on the N torus, the two-dimensional N torus?
On the two-dimensional N torus. So this is harder. So it does have this. So you want to do it on a two-hole torus. Let's say a two-hole torus.
Yes.
Okay. Two-hole torus. Yeah. So I was involved with a paper about single bubbles on the two-hole torus. And yes, I've had students start to look and guess at what might happen. You put the hyperbolic structure on it, right? That's what you didn't want to do. But there can be some possibilities that's not even unique. So it's a very interesting problem, even the single bubble on the two-hole torus.
Ultimately, can we dream of a full bubble profile value with gems?
Yes, all genera, all hyperbolic structures, all possibilities for multiple bubbles, the two-bubble, three-bubble, four-bubble, K-bubble, all in one theorem. Yeah, I can dream of that.
Generating function for that.
We'll name that function after you. It's a function of several variables. Right, that's a good idea.
More questions?
Yes, we got one right here. The guy who was right about not liking something.
In the Gaussian plane case,
Gauss plane, yeah.
Gauss plane case, would, if allowed, a circle around infinity work?
How about a circle around infinity? Well, a circle around infinity is a circle around the origin. You would just want to use the outside of it.
Yeah, would that
You
work?
just want to look at what's enclosed you just want to look at the volume exterior to the circle. Now, that's no better than the volume interior to the circle. In fact, if the circle were minimizing for the exterior volume, it would also have to be minimizing for the interior volume. Otherwise, otherwise any improvement on the interior one would give you an improvement on the complementary exterior one. So no, that's unstable. However, you make a very brilliant observation, actually. The straight line is a circle through infinity. Which leads into many more, which actually is very interesting in terms of something else I'll say a little later, namely at the ICM. But that's a very interesting thing, that circle through infinity, and it leads to many similar conjectures. That the bubble wants to go through the point of minimum density. Yeah.
More questions? Where are triply periodic minimal surfaces here for the three torus? I can't see them.
I see. So you just want to take this. Yeah, each one of these, of course, leads to a triply periodic constant mean curvature. It's made up of constant mean curvature pieces, right? But the pieces can have different curvatures.
Right. There are minimal ones too, right?
Not
in your picture.
Yeah, the double slab here. So this gives you the many copies of the plane. That's a nice triply periodic minimal surface in R3, right? You take infinitely many horizontal copies of the plane. So that's a familiar one here. This one here, no, that's not so good to look at. So you can take that dual and A chain and just continue it. So it keeps chaining. You keep going bubble, 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 a long chain which goes from minus infinity to infinity. And then you get copies of it as you translate horizontally. So that would be
you would
the
guess
corresponding.
that minimal surfaces would give you a better
Minimal ones don't respect the desired volume constraints. That's what we're dealing with here. We're dealing with volume constraints. Now, you want to somehow use these to inspire minimal surfaces?
I was just suggesting to use the ones that are known. Like there's families of...
I see. So take the triply periodic minimal surfaces and try to use them. Yes, take the triply periodic minimal surfaces and try to use them. Well, the Lawson surface, as I mentioned, gets beaten by others in the cubic torus. But if we use the different torus, then it would be useful. So yeah, when we were looking back at the candidates, we did take pieces of triply periodic minimal surfaces, like the Lawson one. Yeah, I guess that's the right answer to your question. And in the cubic torus, they didn't win out.
More questions? Okay, then if not, let's thank the speaker again. Frank, thank you very much.
So,
we're going to have just a short closing sermon.
You're going to say something in a second, but as the last speaker, I have to say, this is our chance to give our final appreciation and thanks to all the organizers, the committees, and especially Claudio and Paolo for all they did to make this meeting possible.